So in this video, I'm going to work through a couple of examples dealing with constant acceleration, which, keep in mind, includes constant velocity. The acceleration is zero. So the first example, we'll look at a Tesla Model S performance. So this car can accelerate from 0 to 60 miles per hour in 2.3 seconds. Notice there's no question, so we'll answer the questions after we model this. So the first thing we're going to need to do is convert the miles per hour because we need everything in meters per second. So we would go through the conversion factor, but this comes out to 0 to, it's 26. Yeah, it's about 26. It's 26 point something. But 0 to 26 meters per second. So we'll be using that. So always meters per second, standard units. And so we can draw a little picture of it. So we can say, the car, which we'll model as a particle, starts from rest. So we would say the initial velocity is 0. And we're going to put time, the initial time, to be 0 as well. And so then this car starts accelerating. So these little velocity vectors will get bigger and bigger. Something like that. And so we could say that the final velocity is this, the 26 meters per second. And that would be at a final time of 2.3 seconds. Okay, so there's a little motion diagram. I didn't label the vectors and stuff. We can say that the acceleration is, in this case, is in this direction because it's speeding up. So these have to be in the same direction. And we're saying that positive is this way. So that's the positive, and it's all moving in the x direction. All right, so now what I'll do is I'll just sketch the graphs. So we'll do position versus time. xt, vt. Oh, and just to state it, we're assuming that it's constant acceleration, but in reality it's not. We're simplifying it to use our model. Okay. So the position, it starts at a position of 0. So that would be at 0. I know I didn't put it there, but the initial position is 0. So we would start at 0, and then we know that it's accelerating, so we know that it's going to be getting faster and faster and faster. And so it would end up here. Now this time right here, we know what that is. That's 2.3 seconds. But if I go over here, I don't know what that final position is. So that might be a question that we can answer. What's the final position? How far did it go when it did this? And then we'll be able to fill in that, and then we'd have a complete graph. For the velocity, we know the velocity is increasing, and we assumed constant acceleration. It starts from rest, so it's going to start at the origin, and it goes up to some final velocity. And here we can go down, and that's going to be 2.3 seconds. And we know what the final velocity is. The final velocity is given. It's 26 meters per second. And then the acceleration. Now we know that the acceleration is to the right, so we know it's positive. And we know that it's constant, so it's going to be something like this. But we don't know what the acceleration is. So we'll just leave that. So that's another question we can answer. What is the acceleration? Okay. So now we can start modeling with some of our kinematic equations. So for the position, we know that the function is going to be x is x naught plus v naught t plus 1/2 a t squared. Okay, now let's substitute in anything that we know to try to simplify it. So the final position, we don't know. We don't know what that is, so that has to stay. The initial position we said is 0, so that just goes away. The initial velocity is 0, so that goes away. So all we're left with is this last part, 1/2 of the acceleration times time squared. That would be the final position. So there's a problem here, is I don't know what this is, and I don't know what this is. So we have two things. I don't know what the values are, so I can't tell you anything about this. I can't tell you XF. I know what the time is. That's the 2.3. So we can't answer that question. So let's go down to acceleration. Can we determine how much acceleration there was? Sure. And we can do the acceleration using the definition. So the acceleration is the change in velocity divided by time. And again, I write it out. Change is always the final minus the initial divided by time. And now we can put our values in there. So on top, we're going to have the final, 26, minus the initial, 0, divided by the time, 2.3. Keep in mind this is average acceleration, but that's all we'll be using. So 26 divided by 3, we get, it's about 11.3. So we get an acceleration of about 11.3 meters per second squared. So now we know the acceleration. So we could say that this right here, this is 11.3. And now I can use that to finish my equation for the position and actually calculate the position. So the final position would be 1/2 of the acceleration, which is 11.3, times the time, which is 2.3, squared. So the distance it covers, I need to calculate this real quick. It's going to be 0.5 times 11.3 times 2.3 squared. That would be 29.89 meters. So it doesn't go very far, but that's because it accelerates very, very quickly. So it doesn't take much distance in order to do that. And so again, now we could just erase that and we could put our 29.89. And our model is complete. So I can't think of any other questions that I can answer based on this model. So let's go on to another example. By the way, I recommend that, well, I guess not for now. No, you're fine. So let's do example 2. Suppose it's going to stop now. So example 2. So the Tesla goes from 60 to 0. So in other words, it stops in a distance of, it's like 100 and something feet, 113 feet. So again, I want to do the complete model before I start trying to answer questions. First thing we'll have to do is change that. So 113 feet is 34 meters. And then 60 miles per hour, again, is 26 meters per second. So those, just to do the conversion. Okay, so what we're doing now is we're stopping. So the car is moving in this direction with an initial velocity of 26 meters per second. And then it stops. Eventually we'll stop doing all these in-between kind of stuff. We'll just do the beginning and end. So, I'm sorry, that should be final velocity. So the final velocity is 0 meters per second. And I know the initial time, we always say that's 0. And then the final time, it's not given, so we don't know what that is. So we could just say question mark. The initial position, we'll say is 0. And the final position is that, 34 meters. It takes 34 meters to stop. Since it's stopping, we know that the acceleration is the opposite direction. So the acceleration has to be this way. So in this picture, since right is positive, I would expect the acceleration to be negative. Okay, so now let's sketch the graphs. So for position versus time, we know that the position is increasing. We know that it's kind of headed in this direction. But the velocity is getting smaller. So it's going to start with some initial velocity, but then that velocity is getting smaller and smaller and smaller. So what we end up with is a quadratic that kind of looks like this until it stops. And we know, we don't know the time, but we do know the position. We know that it takes 34 meters to do that. That's where it'll be when it stops. So now let's go to the velocity. So the velocity versus time, it starts with some initial velocity, so that's up here. And that would be 26 meters per second. And then what it's doing is it's slowing down, so it's going to decrease until it gets to a velocity of 0. And that would, again, take the same time, but we don't know what that is. And then finally, our acceleration. Acceleration over time. And I know that it's working against it, so I know it's negative, so it's going to be down here, and I know it's constant, so we're going to have something like that. But I don't know what the acceleration is. Okay, let's start using our equations and see what we can do. So we'll start here with position. So position versus time is the initial plus the velocity initial time plus 1/2 of the acceleration time squared. And now let's try to simplify anything that we can drop. The final position I know, so that's 34. The initial position, 0. The initial velocity, here, I'll just write it. So that's 0 plus the initial velocity is 26 times t plus 1/2 of the acceleration, which I don't know, t squared. So just simplifying this, I get 34 equals 26t plus 1/2 of a t squared. And now I'm at a block because I don't know what t is and I don't know what a is. So we have two variables and I don't know what they are. We could try velocity. Let's see what that is. Again, what I'm trying to do is answer how much time did it take, and then also what's the acceleration. So those would be the two things. So now let's go to velocity. So velocity is equal to the initial velocity plus the acceleration times time. Well, let's see. I know what the final velocity is. That's going to be 0. The initial velocity is 26. And then plus the acceleration times time. So again, there's two things that I don't know, so I can't solve this equation. You can only solve equations if you have one variable you don't know. So I can't do anything there. Okay, there's only one other option, and this one would make sense because we don't know the time. So when we don't know time, you're usually going to have to jump straight to this one. I'm sorry, that should be VF squared, is V naught squared, plus 2a times x minus x naught. I know I kind of went off the screen there, but I'll rewrite it. So looking at this one, there's no time. I know what the final velocity is. That's 0. And the initial velocity is 26. Plus 2 times the acceleration, which I don't know what it is. But I do know the change in position. That's x minus x naught, which would be 34 meters. Now I have an equation with one unknown, so I can solve for the acceleration. So I would move, this is 0, so I'd move that over. That's negative 26 squared, if I subtract it, equals 2 times 34, which is 68, times the acceleration. And then we divide that. So what I'll get is the acceleration, it's approximately, if I round, is negative 9.9 meters per second squared. So that matches this, and it matches what I thought it would be. It would be negative. So now we can figure out the time. So we can either do this one or we can do this one. I would probably do this one because this one is linear and this one has a quadratic. So it's going to be a little easier to use this one to solve for it. And so we'll plug it in. So we get 0 equals, so we're plugging this in there, 26 plus negative 9.9 times t. Now we just solve for t. So we subtract that over. Negative 26 equals negative 9.9 t. And so then we divide negative 9.9. So the time is equal to, gotta divide that, 26 divided by 9.9, 2.62 meters per second. So now we know the time and we know the accelerator. So we've solved, we have a complete model. And that's kind of, you know, this is, you're not going to do this every time. We're going to do it at first, but eventually you'll be able to just skip and go straight in. But you can always go back and just do it this way and answer any question that you might be asked. The other thing is to make sure that numbers make sense. And so like 2.62, this should be positive because it's time. So if you get a negative time, it's because you dropped a negative. I mean, you left off a negative somewhere. Also, we can think about this. It's 2.62 to stop. And it was, if you remember the first example, it took 2.3 to accelerate to get up to 60 miles per hour. And I don't remember what the distance was. It wasn't very far. But you see, just by going from 0.3 to 0.6, it increased the distance to 34 meters. And I think that's an additional like 10 meters, which is pretty significant. So we can talk a little bit about that, like braking distance and reaction time and stuff. But I'm going to stop there. I'm going to do one more example that's a car chase, chasing vehicles. But I'll do that in a different video because this one's gotten kind of long.